Yeah, so we begin by mathematical induction. So the principle of mathematical induction. So consider consider the set of first n odd positive integers. So consider the set of first n odd integers. So we have 1, 3, 5, 7, 9, 11, all the way up to 2, n minus 1. So I want us to do some experiment. So I want us to do an experiment. Get the sum of the terms. So if I have one term, I'll only have one whose sum will be 1. We only have number 1. Then if we have 2 terms, so 2 terms, we mean 1 and 3. So we'll have 1 plus 3, which will give us 4. So that's the sum. Then if we have first 3 terms, so if we have first 3 terms, I'll have 1 plus 4, plus 3, then plus 5. What do you get? So 1 plus 3 plus 1. 9. Then if we have first 4 terms, I'm going to have 1 plus 3 plus 5 plus 7. So the sum will be 16. If I have first 5 terms, I'll have 1 plus 3 plus 5 plus 7 plus 9. What do you get? 25. Okay, do the same thing and get the sum of the first 6 terms. Sum of the first 6 terms. Or simply having 1 plus 3 plus 5 9 plus 11. What do you get? 36. So without even doing the next one, this case, when we do the sum of the first 7 terms, 49, 8, 64. So that seems to be a trend that we can make an assumption that if we add all these first 5 n terms, then the nature of the solution is likely to be like if we have 1 term, we have 1. If we have 2 terms, we have 4. If we have 3 terms, we have 9. 4 terms, we have 16. All the relationship between the number of first terms taken, the final result. The guess? What's happening? It's like we are squaring, okay? But you have 1 term, sum of the first one, say 2 terms, the answer is 4. So 2 squared. Sum of the first 3 terms, the answer is 9. It can be written as 3 squared. Sum of the first 4 terms, the answer is 16. 16 can be written as 4 squared. Sum of first 5 terms, the answer is 25. So it's like 25 5 squared. So then now when we say the sum of the first 10 terms of this sequence, we can assume or we can make a guess that the answer is n squared. So I guess in mathematics we call them conjectures. So that's a conjecture we make. But so the objective will be, how do we provide the proof of this? How do we really confirm that in general, when we do the sum of the first n odd positive integers, then we must get the value as n squared. So the principle of mathematical induction is a method or a technique that is used to prove such kind of results. But we have this relation that we are doing the sum and we are guessing that the total value of the sum must be given by this formula. So the proof that will actually show that such a sum has this as the final answer will be explained by this principle. So we see the principle of mathematical induction, the principle of mathematical induction is used to prove the principle of mathematical induction is used to prove that a given mathematical statement P of n, that a given mathematical statement P of n is true, that a given mathematical statement P of n is true using the following steps. Using the following steps. So step 1, verify that P of n, verify that P of n is true for n equals to 1. Verify that the statement P of n is true for n equals to 1. So this is actually the initial step. For the first case, and then 2, assume that P of n is true for n equals to k. This is called the hypothesis step. Is the easiest one. What it simply means that now given statement in terms of n, so you change where is n by k, and then we assume that it's true. And lastly, show that P of n is true for n equals to k plus 1. This is called the interactive step, and which is very key in the whole process. So once 1 to 3 are satisfied, we conclude that the statement P of n is true for all positive integers n. So PMI means principle of mathematical induction. So that's the kind of problem that would be dealing with. So you are given a statement, you call it P of n. And then step 1, you show that the statement is true when n is 1. That's the initial step. And then step 2, you assume that P of n is true when you replace n for k. So that's called the hypothesis step. And lastly, you convince us that the statement P of n is also true when you go to the next step, k plus 1. So an appetizer prove that for all positive integers greater than or equals to 1, these are an obvious result, that the sum of first n natural numbers is given by m into n plus 1 divided by 2. So the first step or the 0 step, you actually give the name to the given which you want to. So solution for proof, you say let the statement be P of n is identically equals to 1 plus 2 plus 3 plus 4 all the way plus n is m into n plus 1 divided by 2. So you give the name to the statement. So this means identically. So we are naming the statement that this summation is given by P of n. So step 1. We show that P of n is true for n equals to 1. But remember, there are two sides of this statement. There's the left-hand side which is given as a series, sum of these first n natural numbers, the right hand side, which is given as the formula to get the answer. So P of 1 left hand side, P of 1 will be given by so when remember this is the left hand side from 1 plus up to n, then the right hand side. So P of 1 simply means that I have only one term. So I get 1. I'm only having one term. Then right hand side, I have P of 1 will be given by n, which is 1, into n plus 1, 1 plus 1, divided by 2. So then now, 1 plus 1 is 2. And even a blind person can say that that is 1. So left hand side is 1, right hand side of P of 1 is 2. Therefore, this is true. So since left hand side equals to right hand side equals to P of 1 equals to 1, then P of 1 is true. So that's the initial step. Both sides of the statement will be giving a same value. N is 1. So step 2, we assume that P of m is true for n equals to k. Here there is usually no hard one. So let's P of k equals to 1 plus 2 plus 3 plus 4 plus k, the k into k plus 1 divided by 2. True. So we are duplicating the same statement, only that where there's n we are putting k. And we assume that the statement is true. So then that's step 3. We show that P of n is true for n equals to k plus 1. So this is where we have to convince ourselves that where there's this k, if we put k plus 1, we can play with the whole series to get a solution which will be taking this same structure. And by the way, you should actually see the solution before you start solving it. So if P of k is k into k plus 1 over 2. So what are we expected to have as P of k plus 1? What is the formula? A P of k is k into k plus 1. So P of k plus 1 should be? Oh, that's a hard question. If I gave you y equals to 2x plus 3. So what is, I remember when I write this y is the same as f of x. Y is a function of x. So what is the value of y when x is 1? Okay? Okay? Fine. How are you getting that? You are replacing 1 for it, okay? Yeah. So you'll be the same as f of 1 will be 2, whereas x you put 1, then plus 3. That's how you are getting 5. So same thing here. If when you give k, when you so k is like a machine, give it k, then this is the output. K into k plus 1 over 2. So what does the machine do when you give it k plus 1? What will be the answer? Okay, maybe let's go one by one. Denominator will have 2. Outside the brackets, I'll have k plus 1, correct? Inside the bracket, I'll have k plus 1. This is p of k. So from k, you go to k plus 1. From k plus 1, you go to k plus 2, it is, okay? So this will be k plus 2. So then now, this is what we expect to have as our solution, p of k plus 1. So then the process is now to convince ourselves that we can actually play with that summation such that this is the final answer. So p of k plus 1 will be 1 plus 2 plus 3 plus 4 up to plus k. Then from step k, we go to k plus 1. So that's all we have. Please don't write the answer that we have already found. So that's what we have to show, okay? So that's this now. This p of k plus 1 means that you are getting the sum of the first k plus 1 terms. Now, from step 2, what is the value of that sum? From step 2. Yes? K into k plus 1 over. So this, all this term is the same as k into k plus 1 divided by 2. Because remember, 2 says that let p of k, which is this, be true. So it means that you are allowed to replace all this sum by this formula. Because they say that is this formula is true. So then plus, this is k plus 1. When you know these are two terms, we can always combine them by putting over same LCM. So this will be 2. Then common 2 into just 1. So we have k into k plus 1 plus 1 into 2, 2. Into this, have 2 into k plus 1. Then the numerator will be k plus 1. So this is the same as k plus 1 into k plus 2 divided by 2. So this is what you're saying, that is our p of k plus 1. And that is what we're looking for. So once you get this one, because this formula is actually respecting the same order in which this p of k was obtained. So you have p of k, then you get k into k plus 1. And then here, p of k plus 1 is with k plus 1, then the next step, which is k plus 2. So then once you have this one, then you say, therefore, by the principle of mathematical induction, the given statement is true. If you have time, you can derive the same thing. These sums, the original sum, 1 plus 2 plus 3 plus all the way up to n. 1 plus 2 plus 3 all the way plus n. It's actually n into n plus 1 over 2. So this statement is. So let's see the other problem. Prove that three raised power 2n plus 2 minus 8n minus 9 is divisible by 8 for all n greater than or equals to 1. But by default, this n is always taken to be positive natural. So let's show that that given expression is always divisible by 8 for all positive integers greater than or equals to 1. So the proof the zero step is to name the statement as P of n. So let's P of n be the statement 3 power 2 n plus 2 minus 8n minus 9 is divisible by 8. If you like, you say x relevant. So this is the statement now. So you name the statement you want to prove as P of n. So then step 1, show that P of n is true for n equals to 1. So that P of n is true for n equals to 1. So P of 1 is 3 raised power 2 times 1 plus 2 minus 8 times 1 minus 9. So this is the same as, so 2 by 1 is 2 plus 2 is 4 minus 8 minus 9. So can you tell me what is the value? 64. So this is 64, and everyone can actually see that. So P of 1 is true. So 64 is a number 8. So the P of 1 statement is true. Then step 2. We assume P of n is true for n equals to k. So assume or suppose P of k which is 3 raised power 2 k plus 2 minus 8k minus 9 is divisible by 8. So it's true. So we're saying that we are assuming or taking or making K to be true statement. So this means that we have the same statement, but we place n by k. So assume that that statement is true. So that is enough. That's what's the true just by replacing k and saying that the statement is true. So therefore now we have to show that this statement P of n is also true for f of n equals to k. So step 3, show that P of m is true for m equals to k plus 1. So that's where the work is. So P of k plus 1 will be equals to 3 raised power 2, where this n we put k plus 1, then it was plus 2, minus 8m, so 8 into k plus 1, then minus 9. That's what we have. So in short, we have everyone that this expression is divisible by 8. So this is 3 power 2k plus 2 plus 2 minus 8k minus 8 minus 9. So then now the powers, this can be written as 3 raised power 2k plus 4 minus 8k. Now minus 8 minus 9, minus 17. Minus 17. So what do we do next? When you see such a natural, what will come into your mind? Natural. Remember, the previous step was that we assumed 3 raised power 2k plus 1 plus 2 minus 8k, then was it minus 9? But minus 9 is divisible by, it's like 8 divides this. This is what we have assumed instead. So we have to be very smart. The question we have, we ensure that we play with it in such a way that we can have this expression. which we already know that is divisible by 8. Okay? This is already known to be divisible by 8 from the step 2. So you can rearrange this one as, instead of factoring, putting these ones together, we can write this one as 2 raised power 2k plus 2 times 3 power 2 minus 8k. We can keep our minus 9 and then minus 8. So we are just we are able to take care of this expression whose relationship with 8 is already known. So this, we can have this as 3 raised power 2 into 3 power 2k plus 2. Then what we do is just force all these expressions into the equation. So we'll have minus 8k minus 9. Then we had here minus 9 minus 8. So what should we do to this so that it's the same as the original? Well, remember, this is not exactly the same as the previous expression. So what should I add or subtract to ensure that I have the same 3 raised power 2k plus 2 times 3 raised power 2 minus 8k minus 9 minus 8. What should we do? What should you add or subtract so that we have the same expression in the previous step? So let's go term by term. If I was to open these brackets, then 3 power 2 times this first term, there's no problem. It's exactly what you have in the previous step. Okay? So that one, there's no problem with it. And then 3 squared and minus 8k. So what should I do to balance? Remember, initially I only had minus 8k. So what should I do so that I don't interfere with the value of this part involving k? Okay, by the way, this is just 9. There's nothing like I have 9 times minus 8k. So this gives us minus 72k. Okay? I think that. But if I multiply this by this one, all this line will have minus 72k. But what did we have initially? Minus 8k. So how do I convert minus 72k back to 8k? I should add more. Positive 64. So plus 64k. Okay. So we'll have already taken care of terms involving k, because when I open this, I'll have minus 72k plus 64k. I get minus 8k. Then this is 9 times minus 9 is minus 81. But initially we had here minus 17. Okay? These two constants give us minus 17. So how do I balance so that I still have my what should I do? What should I add? What should I, so that exactly I have, if, by the way, this can as well be minus 17 if you put it. No. So what should I have? To have the constant being minus 17. What is that? 64. Huh? 81. 81. 81? Yeah. Okay. So you see what is happening is that this part is the same thing in the previous step, okay? Now, when we introduce brackets here, the strange value we are adding is minus 81, okay? So that we don't have it, we need to add it. So minus 81 plus 81 is 0, okay? Yeah. So then now we have, so this would be 3 power 2 into 3 power 2k plus 2 minus 8k minus 9. So what is minus 9 minus 8 plus 81? 64. So plus 64k plus 64. We are not worried in this part because this part is given by, yeah, because this, if you have multiplied two numbers and one of the numbers is divisible by the divisor, then the whole product is divisible. So this can as well be written as 3 squared into 2k plus 2 minus 8k minus 9 plus, just to make my, I can say this is 64 into k plus 1. Because this part is divisible by 8. 64 is also divisible by 8. So which is divisible by 8. So we have successfully confirmed that v of k plus 1 is an expression which is divisible by 8. For this is divisible by 8 from step 2. This other part is also divisible by 8 because 64 is a multiple of 8. So therefore, by principle of mathematical induction, 3 power 2m plus 2 minus 8m minus 9 is divisible by 8. So I want you to try this. So use mathematical induction to prove that. Use mathematical induction to prove that. For any integer n greater than or equals to 2, 3n squared is strictly greater than n plus 1 squared. So show that for any integer n which is greater than or equals to 2, then 3n squared greater than n plus 1 squared. Okay, this is where now common sense comes in. So the first step in the mathematical reduction proof. Remember, we say that we start by confirming P of 1 is true, then go to P of k, then confirm P of k plus 1. So here, the question has restricted you to start from 2. So this is that will be a starting point, okay? So the initial step will be now to confirm that P of 2 is true. So it's not now P of 1. So get that one correct. But because there is already a restriction in the question itself that the smallest integer is 2. So then the initial step will be confirming that P of 2 is 2. And then the rest follows.